All right, everyone, we had a number of questions for homework last night on page 168, questions number 1 to 8. Any issues with any of those questions on 168, please? I know that some of you do, because some of you had a couple blanks as I was checking it over. Guthrie? 2B, yeah. You got number 3 as well, 2B and 3. Any others going once? Nope. 8. 2B, 3, and 8. Going once, going twice. Okay, let's do question 2. Let's do both question A and B for number 2, okay? 2 says, explain why a swimmer at the edge of a pool pushes backward on the wall in order to move forward. Why does a person swimming in a pool wanting to go forward push backward on the wall? What does that come down to that we've been talking about for a few days here now? Yep. Newton's third law, which says if object A applies a force on object B applies an equal and opposite force on object A. So you pushed on the wall pushes on you. Okay, you push backward on the wall pushes forward on you with an equal and opposite force. B says when a person in a canoe throws a package onto the shore, the canoe moves away from the shore. Why does that happen? As you push on the package, the package pushes back on you. You're inside the canoe. So if you throw the package, let's say to the east, which way is the canoe and you going to be pushed? To the west with an equal and opposite force. Now, it doesn't mean you're going to go as fast as the package did. Can anybody explain to me why when you throw that package to the shore, it might go quite fast, but yet you might be pushed backwards pretty slow? Didn't we say the forces always have to be equal and opposite? You do. So why do you move slower than the package moves? Who's got that one for me? Jazzy just says, because the person can take more force than the package. Kind of. Why can we take more force than the box? Not because we're stronger than the box is. The box isn't breaking here either, right? But we still can kind of take more force than the box. What were we going to say there, Luis? Yeah. In the end, if you apply a force on something that has a mass of 1 kilogram and apply the same force on something that has a mass of 70 kilograms, the 70 kilogram mass is going to accelerate less. So even though you push on the box pushes back on you with the same force, you accelerate slower because your mass is greater. Got it? Okay, so let's pretend you're an astronaut for a second. You're doing a spacewalk. You're out in space, okay, you're doing a spacewalk, and somehow you get untethered from the space station. So you're floating free in space. Do you know, by the way, when you're floating free in space, everyone thinks, oh, you're sitting there in space. You're not sitting there in space. You're actually orbiting around the Earth at about 30,000 kilometers per hour as you sit there in space. And the space station orbits around the Earth at about 30,000 kilometers per hour as well. How do you get back, though? How do you get back to the space station? If you're floating away, you can't get back? Well, it's not inconceivable that you could get back. It would be a very difficult proposition to get back, but it's not inconceivable. You're both moving at about the same speed, about 30,000 kilometers per hour. So in other words, relative to each other, you're pretty much at rest. So how do you get back? You take the baseball out of your pocket and you throw it. Which way do you throw it? If the space station is over there and I want to get over there, which way do I throw the baseball? Throw it that way, right? Throw it the opposite way. When I apply a force on the baseball applies a force, equal and opposite force back on me. Now, the baseball's going to accelerate at a much greater rate because it's lighter, but you're still going to accelerate as well. Hey, how about this one? And then we'll move on to question number 3 here. What can you describe for me, please, the action-reaction forces involved in an airplane moving forward? Okay, what does the airplane push on, and then what pushes back on the airplane? The airplane pushes on the air, pushes out on the air, right? The air pushes back on the airplane, is that right? No, not at all. So what is it? What does the airplane push on? Why does the airplane burn fuel? It pushes on exhaust out the back of the airplane, right? The airplane pushes back on the exhaust. What's the reaction force? The exhaust pushes back on the airplane. So it's not the air that's pushing the airplane forward. In the case of jet, at least, it's the exhaust pushing the airplane forward. Does that make sense? What produces the thrust? It's not the air. What produces the thrust is the burning fuel going out the back, pushing it forward. Okay, let's take a look at number 3 here now. No matter how powerful a car engine is, a car cannot accelerate on an icy surface. Use Newton's third law, and maybe that figure on 161, but especially Newton's third law to explain why. No matter how powerful the car is, you can't accelerate on an icy surface. How come? What force do the tires apply on the ice? What's the force of friction that the tires apply on the ice? Yes, but how much? What's the value of it? Basically, zero force of friction, right? If you apply a force of 0 on the ice, how hard does the ice push back on you? 0. Right? A car works by applying a force on the road. What is the force? What happens to that force now? Well, it gets returned. If the tires apply a force on the road backward, then the road applies a force on the tires forward. If you can't apply the force backward on the ice, then the ice can't apply the force forwards on you. So by Newton's third law, okay, since there's no action force, there's going to be no reaction force as well. Finally, we have number 8 here. It says blocks X and Y are attached to each other by a light rope and can slide along a horizontal frictionless surface. X has a mass of this value, Y has a mass of this value. We have an applied force to the right of 36 newtons. 10 kilograms and 5 kilograms. We want to know the action-reaction forces the blocks exert on each other. Well, if X pulls on Y to the right, then Y pulls on X to the left, right? We know what happens in both of those cases. We just don't know the values of the forces. We'll figure those out in a second. Now, B says, suppose the magnitudes of the force of friction on the blocks X and Y are 8 newtons and 4 newtons respectively. Now let's get the action-reaction forces the blocks exert on each other. So basically we have 2 questions here. Okay, what's the force in between there right now? And what's the force become if I add forces of friction in there? We know what to do here first, right? We've done these for a few days here now. We have to find the acceleration of the system first. Look at the whole thing first. The external, the big picture, the back of the semi-truck versus the ice cream within the semi-truck. Let's say the net force is equal to the sum of the forces. There is only one force acting on the system here. It's the applied force. So let's say M times A is equal to that applied force. And the mass here is going to be 15 kilograms. So it's going to be 15 times A is equal to 36. 36 divided by 15 is 3.4 meters per second squared. Okay, we're not done. Now we've got to find the force in between. To find the force in between, is that wrong? Did I make a mistake there? Is it 2.4? Yes, it is. Yeah, you're right. Thank you. 2.4 meters per second squared. Now to find the force that acts between them, what am I going to do? Did a couple of these yesterday, did a couple the day before that. Pick an object. Does it matter which one? Usually we want to pick an end object. Both of these are end objects, so it doesn't really matter which one we pick. I'm going to pick the 5 kilogram object. Okay, you could have just as easily picked the 10 kilogram object. There is only one force acting on the 5 kilogram object, and it's to the right. It's the force of X on Y, and that's what we're trying to find. The net force is equal to the sum of those forces. It's just the one. The net force is M times A, but this time the mass is going to be 5. because we're only analyzing the one object. The acceleration will still be 2.4. Fxy is what we're going to solve for here. 5 times 2.4 is going to give me, had you calculated the force of y on x, you would have got negative 12 newtons. So the action force, 12 newtons, the reaction force would have been negative 12 newtons. I don't care which one you give me. All right? It's going to change now that we have friction acting in here, though. Let's draw that in. On object number y, on object y, we have a force of friction of 4 newtons. We'll call that FF1. On object x, we have a force of friction acting to the left of 8 newtons. We'll call that FF2. Let's analyze the whole system here again to find the acceleration of the system. The net force is equal to the applied force plus FF1 plus FF2. The mass here is 15 times acceleration is equal to 36 to the right plus negative 4 to the left plus negative 8 to the left. 36 subtract 12 is 24. 24 divided by 15 is 1.6 meters per second squared. What was the acceleration the last time? I can't remember what it was. What was it? Oliver, did you have that? It rings a bell, actually, 2.4. Why is the acceleration less this time? Should it be less? Is this a reasonable number that we should expect to get? Yes, why? Right, exactly, there's friction. It's going to accelerate at a lower rate if there's friction acting, right? How much less? We don't really know until we get a number, but we know that it's going to be less. All right, now let's analyze one object. Let's pick the 5 kilogram object again, although it doesn't really matter. Okay, we've got a force of friction acting on it, FF1, that's 4 newtons. And we have a force acting to the right, that's the force of x on y. The net force is equal to the sum of those forces, FF1 plus Fxy. The mass is 5. The acceleration is 1.6. Ff1 is negative 4. And Fxy is what we're looking for here. 5 times 1.6 is 8. 8 plus 4, take the 4 over by adding, gives me 12. And Fxy equals 12 newtons. Okay? Make sense? Yep.
Does that mean that that's like how hard object Y is pulling back?
Yes. Yeah, what we've actually calculated here is how hard object Y is pulling on, object X is pulling on Y. But if object X pulls on Y with a force of 12 newtons, logically, let's think about that for a second, okay? If you apply a force of 36 newtons on object X, well, that force isn't directly being applied on object Y. Object Y has got to be pulled by something, though. It's being pulled on by object X. We've just calculated that force that object X pulls on Y with. Now, by Newton's third law, if X is pulling on Y with that force, then Y is also pulling on X with that force. So when does that come into play? When does that become an issue? Well, let's say that you've got this rope that joins object X and Y together. And let's say you've got this, this connector here, this bracket that joins the rope to object Y and this bracket that joins the rope to object X. Okay? Is it possible that that rope could come disconnected from that connector? Could it break from that connector break and separate right here? Of course it can, right? But why can it separate right there? If object Y is not pulling back on object X, then the rope isn't going to break right there. And it's not going to separate right there, right? Intuitively, though, we know that it can. Again, why? Because object Y is pulling back on object X with the same force that X is pulling on Y. Does that make sense? Now, which one you find doesn't matter. Okay, you analyze object X and you get negative 12 newtons, that's fine. You analyze object Y and you get positive 12 newtons, that's fine as well. Okay? You good with those? I think that was it, 4, wasn't it? 2, 3, and 8, yeah. Excellent. All right, let's do another example problem involving multi-force problems, okay? Over the next couple of days, that's what we're going to be doing is various applications of multi-force problems. Not necessarily the question where, we had on our quiz where we've got, one guy pulling it one way, one guy pulling it another way, and friction pulling it one of those two ways. But rather, maybe we got gravity acting in a normal force, or maybe we got two other forces acting. Same idea, except different forces, perhaps. Okay, so we're going to take a look at a number of different possibilities that we might see, a number of different applications that we can see, including the elevator problems that we did yesterday and the elevator problem that we're going to do here right now in 3.7. It says, a person and an elevator have a combined mass of 600 kilograms. The elevator cable exerts a force of 6,500 newtons upwards on the elevator. What's the acceleration of the person? This is a little bit different than yesterday's problem. Remember yesterday's problem, guys? We had a guy in an elevator. We had a force of gravity acting down on the guy, and we had a normal force acting up on the guy. Well, we still do on the guy inside the elevator in this question, but that's not what we're trying to analyze this time. We don't want to analyze the guy in the elevator. We want to analyze the elevator itself. Now, there's still a force of gravity acting down on the elevator. What other forces do we have here acting on the elevator? Right, acting on the guy, there's the floor, but we're not analyzing the guy. What other forces act on the elevator itself? It's kind of staring you in the face if you read the question again. How does the elevator not plunge down to the ground? How, when you're in an elevator, do you not plunge to your death when you're on the 100th story of a massive skyscraper? Okay, what pulls it up? Yeah, we can call it the normal force if you want. Call it the force of the cable if you want. It doesn't really matter what you call it. In the end, there is a force pulling the elevator upwards. Now, sometimes that force of the elevator upwards, force on the elevator upwards, may be greater than gravity. Sometimes it's less. If it's greater than gravity, then the elevator accelerates upward. If it's less than gravity, the elevator accelerates downward. Okay, in this case, we know that the force the elevator cable exerts upward, I'm going to call that Fc, the force of the cable, is 6.50 times 10 to the 3 newtons. Now, Dustin called it the normal force. Could he have named that Fn instead of Fc? Sure, it doesn't matter what you name it, right? Okay, in the end, it ends up being the same thing there. Force of gravity, by the way, is going to be 600 times 9.81, which I think is 588.6. All right, let's do our thing here. The net force is equal to the sum of the forces. In this case, it's Fc plus Fg. The net force is m times a. The mass here is 600 kilograms. The acceleration we're trying to find. Fc is 6.50 times 10 to the 3 newtons. And Fg is negative 588.6. Negative because it's acting downwards. Let's solve for a here. Let's pull out the calculator to do this. So we've got here 6,500. On the right side, subtract 588.6. Now let's divide that by 600. We get 9.85. That's a big, sorry, go ahead. Yes, it would actually. 5,886, yes. That actually makes me feel better, Thomas. Thank you for that, because I didn't like that number that I just got there. Why didn't I like that? It's a big acceleration. Can you imagine you're standing in an elevator and it's accelerating upward at the same rate as you accelerate downward? That's like free falling, except free falling upwards instead of free falling downwards, right? You don't get too many elevators that are accelerating at that rate. Okay, so let's try that again now. Let's try the math again. So we're going to say 6,500, subtract 5,886. Now let's divide that by 600. It's going to give you a much better number here. Yeah, that's better. 1.02 meters per second squared. So you're accelerating upward at a rate that is about 10% of gravity. So this isn't nearly as bad. That's much more reasonable, right? How is this question different than the question we did yesterday? The elevator problem with the guy inside? Not much. We're just drawing a free body diagram for the elevator instead of the guy inside. How is it different than the quiz question you did earlier today? Not much, except the forces on that quiz question were guy pulling one way, guy pulling the other way, friction pulling to the right. Okay. Here it's the same thing. Guy pulls up, guy pulls down, find the net force, set it equal to m times a. Make sense? The beauty of this method that we're using to solve problems now, this whole net force thing, this free body diagram net force thing, is that it applies to so many situations. Once you learn it, you can do the quiz question, okay, horizontal, and you can do, an elevator problem, and you can do completely different things because you have a technique, you have a method now, right? Let's take a look at these two questions that you see on 152, please. Give you a couple minutes to work on those, and we'll see if we have time for one more example when we're done these. All right, guys, let's take a look at question number 2 here. A lot of people are having a little bit of trouble with this one, not because of the concept involved, but because of the mathematics involved. It's a little bit tricky here. We have an electric chain hoist in a garage exerting a force on an engine. Here's my engine. Okay, the force upwards, we'll call it the force of the chain. It's 2.85 times 10 to the 3 newtons. We also have a force of gravity acting downwards, and we don't know what its value is. We know it's smaller than the force of the chain because it accelerates upward, so the upward force has to be bigger. Gravity is m times g, m times negative 9.81. All right, let's set it up here. F net is equal to the sum of the forces. That's Fc plus Fg. F net is m times a. The acceleration is 1.50. Fc, we were given the value of the force of the chain is 2.85 times 10 to the 3 newtons. And the force of gravity is m times negative 9.81, mass times gravity. Now, our problem is that we've got m in 2 places here, right? What do we do with that? Well, we combine them. We combine like terms. If you have 1 apple over here and you have 2 apples over here and we want to combine them, we end up with 3 apples, right? We're combining apples. 1 plus 2 is equal to 3 apples. If we have 1m over here and 2m over here and we want to combine them, we end up getting 3m's, right? Well, if we have 9.81m over here and we have 1.5m over here and we want to combine them, let's add them together. Okay, this goes to the other side by adding, because it is a negative term on the right-hand side. So it's 1.5m plus 9.81m gives me 11.31 m. All I'm doing is adding 1.5 plus 9.81. That's my coefficient, and then that's times m. Yep. Okay, why isn't it m squared? Can anybody answer that question? Why is it not m squared? Yep. Right. If we were multiplying the numbers, m times m is m squared. M plus m isn't m squared. Right? M plus m is 2m. Or 1.5m plus 9.81m is 11.31m. But not m squared because its addition is opposed to multiplication. All right? So we divide that now. 2.85 times 10 to the 3 divided by 11.31, we end up with 252 kilograms there. Does that make sense? All right, we don't have time to do this example problem, guys, but I think that you can still answer these next 2 questions that you see on page 153. So what I want to do is assign those 2 questions for homework, please. Questions 1 and 2 on page 153. See what you can do with those. We'll take a look at them tomorrow, and we'll go from there. Remember, tomorrow you also have a quiz, but your quiz tomorrow is on finding that force between 2 objects, right? Yeah, I'm telling you right now what the question is going to be. Here's 2 objects. Maybe you got a force going, a couple forces going on here. We want to find this force right there that acts between those 2 objects. Okay? All right, that's it for today, guys.